Hello students, in this video we will discuss about the retrosynthetic analysis of the molecule. This is the molecule that is given to us. See, this is the molecule that is given to us. This is the target molecule. This is our target molecule. Now we are writing the retrosynthetic analysis. Retrosynthetic analysis. Okay. First of all, the first step is that we will write down here CN-amide disconnection. This is CN-amide disconnection. CN-amide. See, from here onwards I'll write this group as a pH. So PHCH2, CHOH, and then CH2, CH2, C double bond OCl plus methylamine. Now this C double bond OCl is obtained from PHCH2, CHOH, and then CH2, CH2, C double bond OH. Okay. Now how to disconnect this molecule? See, this retrosynthetic analysis is a little bit interesting. And then we'll disconnect here. Once we disconnect here at that particular place, then we'll have PHCH2OH, CH2 plus, and then we have CH2 minus C double bond OH. Now the synthetic equivalent for this CH2 minus C double bond OH is diethyl malonate. CH2 C double bond OC2H5 and then C double bond OC2H5. This is the diethyl malonate. The synthetic equivalent for this is an A2 synthan, and therefore the corresponding A2 synthan is nothing but PHCH2, and then this is nothing but an epoxide. And then how this epoxide is obtained? This epoxide is obtained by PHCH2 CH double bond CH2. So this is alkene. If you wanted to have an epoxide, you need to have an alkene. Now how this alkene is obtained? This is what we call it as epoxidation. And then here we have PHCH2 C double bond OH plus we have PH3P double bond CH2. See, this is nothing but your Wittig disconnection. This is Wittig disconnection. Now how this is called phenylacetaldehyde. This is called phenylacetaldehyde. There are so many methods are available with us to synthesize this phenylacetaldehyde. One method is this. So therefore we'll disconnect here. Then we'll get HC double bond O minus plus we have PHCH2 plus is identically equal to PHCH2Br, and this is D1 synthan. Now the synthetic equivalent for this is dithiane. So starting from dithiene, we'll synthesize the phenyl acetaldehyde, then we'll do the Wittig reaction, then we'll do the epoxidation, and then we'll treat the epoxidation with the anion of diethyl melanate. This is called diethyl melanate. This is diethyl melanate. Okay. Now this is all the retrosynthetic analysis, and therefore now we'll go through the synthesis. Now we'll go through the synthesis of this molecule. First, let us start with 1,3-dithiene. N-3-dithiene on treatment with N-butyl lithium. N-butyl lithium. N-butyl lithium will abstract this proton to give a dithiene anion. Dithiene anion. Now this is not treated with CH2Br benzyl bromide. Benzyl bromide, this is an SN2 reaction. This is yes, this is yes. H, CH2PH. Now this is now hydrolyzed in the presence of aqueous solution of mercury chloride. Now that gives rise to pH, CH2, C double bond OH. So this is the first step. So this is the step 1 of the reaction, and then now PH3P triphenylphosphine reacts with methyl bromide by an SN2 reaction. By an SN2 reaction, then we'll have PH3P plus, and then this is CH3. Now this hydrogen is abstracted by treating with N-butyl lithium again. So we'll get an ylide, a phosphorus ylide. And if we write a resonance structure for this, then we'll get the phosphorane form. So this is what we call it as methylene triphenyl phosphorane. Methylene triphenyl phosphorane. Okay, so now in the next step, let us start with this PHCH2 C double bond O, PHCH2 C double bond OH, PHCH2 C double bond O H, plus we have PH3P double bond CH2. So this is a Wittig reaction. This is a Wittig reaction. Now therefore we will get PH CH2 CH double bond CH2. We will get hydrogen here, and then this PH double bond CH2. Now this is now treated with an MCPBA, metachloroparabenzoic acid, and that gives rise to an epoxide. Now we have diethyl melanate is there, CH2 C double bond O, OC2H5, and then this is C double bond O, OC2H5. Now this on reaction with your ethoxide ion Because this is active methylene group, this particular proton is acidic in nature. So therefore this gives rise to a resonance stabilized carbanion. CH minus, C double bond O, OC2H5, C double bond O, OC2H5. Now, in the next step, we'll react this diethyl aluminate anion with this epoxide. Now, the epoxide PHCH2 CHOO. Now that reacts with a diethyl aluminate anion CH minus C double bond O OC2H5 CH minus C double bond O OC2H5. So this is an SN2 reaction. Reaction takes place at the less hindered side. Reaction takes place on the less hindered side. Less hindered side of the epoxide. So PHCH2 CHO minus, and then we have CH O minus CH2. This is CH. This is the new carbon-carbon bond formed. This is the new CC bond. New CC bond formed. CH C double bond O OC2H5, and then we have C double bond O OC2H5. So this on number 1 is hydrolysis, OH minus comma H2O, followed by H3O plus. We'll get PH CH2 CHOH CH2, and then see here we'll get a diacid. Now this is a malonic acid derivative. Now this on heating it undergoes decarboxylation easily minus CO2, and that gives rise to pH CHOH CH2, and then we have CH2, and then C double bond O OH. Now this CH2 C double bond O OH on reaction with SOCl2 we'll get pH CH2 CHOH CH2 C double bond O Cl. So here the acid is more reactive. Acid is more reactive than alcohol. So therefore acid is more reactive than alcohol, so therefore we'll get this OH, therefore we'll get this C double bond Cl here. Now this reacts with the methylamine, minus HCl is lost, and then we'll get this product PHCH2 CHOH, and then CH2 C double bond O NCH3. So this is our target molecule. So this is the last step. See here in this particular step, see phenyl acetaldehyde is a well-known starting material. So therefore we can purchase this starting material, or we can synthesize by this method. So this is I only told you about the synthesis of this because to know chemistry and to enjoy the chemistry. So like this, similarly, this phenylacetaldehyde molecule, this is phenylacetaldehyde. This phenylacetaldehyde molecule can be synthesized by another 4 methods. 5 methods are there to synthesize. 5 different methods are there to synthesize this phenylacetaldehyde. The chemistry is so fantastic for the synthesis of this phenylacetaldehyde molecule. So therefore, this is overall synthesis. And then I'll also give you another synthetic strategy for this. The path 2, second path. This is path 2. Again take this molecule PH, CHOH, CH2, CH2, C double bond O, N, CH3. This is my target molecule. Okay. Now here again this is obtained from, this is CN-amide disconnection, PH, CH2, CHOH, CH2, CH2. This is C double bond OCl, and this C double bond OCl is obtained from PH plus methylamine, of course. Here this is methylamine, PH, CH2, COH, CH2, CH2, C double bond O, OH. Now let us write down the retrosynthetic analysis for this. Now what I'll do is that I'll just disconnect the molecule, and then now we'll write down another one here. This is FGI, functional group interconversion for this. So functional group interconversion for this, OH is obtained by the reduction of C double bond O. So this is C double bond O, CH2, 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 and then C double bond O, OH. Now this I will disconnect the molecule here. Once I disconnect the molecule, I'll get this PH, CH2, C double bond O, CH2 minus, and I will get CH2 plus, C double bond O, OH. See here, the synthetic equivalent for this will be alpha halo acid. See, generally we won't do the reaction with acids, so therefore what I will do is that I'll take the alpha halo ester, then we'll hydrolyze to get the acid, C double bond O, C2H5. We'll start with this. Now the synthetic equivalent for this is this PH, CH2, double bond, see this is NMN, this is an NMN. Now this NMN can be obtained from, PH, CH2, C double bond O, CH3. This is NMN. So less substituted NMN is formed here in this. Less substituted NMN. Methyl benzyl, this is benzyl methyl ketone. Let's substitute NMN. See here we can also write the synthesis of this. If we want, you can also do the synthesis of this. Very simple method, again by using diethane chemistry. See here, if I disconnect the molecule here, then I will get CH3, C double bond O minus. See, this is D1 synthon, and PHCH2 plus, and the synthetic equivalent for this will be equal to PHCH2Br. And the synthetic equivalent for this is a substituted diethiene. So we'll start from this. We'll start from this molecule, and then we'll do the alkylation and then hydrolysis. We'll give you this. From this we'll do the NMN. So let us go to the synthesis step by step. No synthesis. Okay, first let us start with the substituted dithiene. So this on treatment with your n-butyl lithium, it abstracts the proton, and then we'll get this CH3, CH3, this is Li. Or we can also write, we'll get the dithiene anion. This is CH3 and I'll get an anion here. Now this anion on SN2 reaction with benzyl bromide CH2BrPH, this is SN2, Br is lost, and then I'll get S, CH3 here, and then CH2PH here. Now this is now hydrolyzed by using aqueous mercury chloride solution. So therefore I'll get CH3, C double bond O, CH2PH. So I've got the benzyl methyl ketone. Benzyl methyl ketone is formed. If the starting material is readily available, directly we can start with this. There is no need to synthesize this. Directly we can start with this material. So this is the first step. I am only giving you the synthesis of this, that's it. Now pH, CH2, C double bond O, CH3. Now this on reaction with an NMN. In NMN, on treatment with the pyrrolidine in the presence of para-toluene sulfonic acid, PTS, then here this is an unsymmetrical ketone, so therefore here we will get a less substituted enamine. Less substituted enamine is formed. Less substituted enamine is formed. This is the less substituted enamine. I am not writing the mechanism of this because this is a well-known reaction. Less substituted enamine is formed. Okay, next alkylation of this enamine now. So pH, now this less substituted enamine is now alkylated with alpha haloester. BrCH2 C double bond OC2H5, and we know that pretty well that this is also an SN2 reaction. So we'll get pH, CH2 double bond N plus and then CH2. See, this is CH2 and then C double bond OC2H5. So this is the new CC bond that is formed. New CC bond formed. Okay. Now this on hydrolysis. Simple hydrolysis, H3O plus will give you this pH, CH2, C double bond O. Only this is iminium ion. Iminium ion is only hydrolyzed here. Iminium ion. Only iminium ion is hydrolyzed. CH2, CH2, C double bond O, C2H5. Then in the next step, what we'll do now is that this ester is hydrolyzed completely. OH minus comma H2O. and then this is now hydrolyzed completely, H3O plus. So pH, CH2, C double bond O, CH2, CH2, and then this becomes a C double bond O, OH. C double bond OH, and at this stage this is C double bond OH, and then this is C double bond O. Now we want OH here, so what we'll do is that we'll treat this with SOCl2, pH, CH2, C double bond O, and then CH2, CH2, C double bond O, Cl. Now this is now treated with methylamine. So we'll get pH, CH2, C double bond O, CH2, CH2, and then C double bond O, NCH3. Now here there are two different groups are there. I want to reduce only the keto group without reducing the amide group. So I'll use a mild reducing agent, sodium borohydride. So once we use sodium borohydride, then we'll get the target molecule. So this is our TM. This is how we can synthesize this molecule. Thank you. We'll discuss another synthesis of another molecule in the next video. Thank you.